Alright guys, today we are starting Hess's Law. We're going to do the first part of chapter 10.1. So we're going to split it into two parts today. So we use calorimetry most of the time, however not all experiments can be used, not all enthalpies can be found using calorimetry. Some because they aren't dilute solutions. So remember that when a dilute solution is used, we can use the specific heat capacity of water, but when they start to become too concentrated, the ions and particles in the solution start to affect that. Sometimes the reaction's too slow and you can't actually measure a temperature change. You're actually going to start losing temperature and heat to the surroundings, or the reaction can be too powerful. So for instance, the thermite reaction, you're going to need some pretty strong metal to keep that contained. So in that case, we can use Hess's law. So Hess's law says that the enthalpy change of a physical or chemical process depends only on the initial and final states and is not dependent on whether the reaction is made in one or multiple steps. So this basically says that I can add as many different reactions, or there can be different side reactions happening, as long as we always reach the same products from the initial reactants. The change in enthalpy will always be the same. So you can think of this as vectors. It doesn't matter how many vectors you add together, as long as they end up at the same place. Your overall distance for it, or change in distance, would be the same. So we're going to do this two different ways. Today we're going to do adding reactions, and tomorrow we will practice using a formula. All right, so adding the reactions. We're going to start by looking at the reaction for photosynthesis here. So if we compare photosynthesis and cellular respiration, we can say that they're the opposite. They're not totally the opposite, but today we're just going to consider them that. And they're not totally opposite because of the state of the water. Okay, so if we were to write out cellular respiration, I'm going to look at the thermochemical equation here. So if I flip the reaction and have 6O2 plus C6H12O6 making 6 water molecules, 6 CO2, and we get that energy term again. All right, so now when I flip the reaction, it becomes exothermic. So if I wanted to take a look at writing it in delta H notation, I would just say delta H is equal to negative 2802.5 kilojoules. All right. Okay, so I'm going to use this information, and I am going to find the enthalpy change for this reaction. Okay, now no information is given, so I can't do Q equals MC delta T or anything like that. So what we're going to do is we're going to take a look into our data booklet, and you can see that there's a page and it says standard molar enthalpies of formation at 298.15 Kelvin. All right, so there's a list of compounds, the formulas, and it says delta FH, the little zero. So that's the enthalpy of formation at standard conditions. Okay, so formation means I can write that formation reaction, and that will be the exact delta H for that reaction. So I'm going to start by writing the formation reaction, for each of these compounds here. All right, so these are my reactions, and I can look up the enthalpies of formation in my booklet. So for calcium oxide, you'll find that delta H of formation standard conditions should be negative 634.9 kilojoules. Okay, and it's per mole, but I wrote the equation per 1 mole of calcium oxide being formed. For water as a liquid, be careful of the state that you look up for water because there are two states listed there. All right, I should have negative 285.8 kilojoules. And last but not least, for calcium hydroxide, if you look that up, it is negative 986.1 kilojoules. All right. Now, all of these can be used to make my final reaction. So what I'm going to do in Hess's law is I'm going to use these reactions and add them in any way, so whether they're in the forward or the reverse form, to get my final reaction here. So what I'm going to do is I look here and I say, okay, I'm going to look for calcium oxide. I find it in this reaction here, but it's a reactant in this one and it's a product here. So what I need to do is I need to flip this reaction and I'm going to get calcium oxide as a reactant then, okay? And because there's a 1 in front of this and a 1 here, I don't actually have to multiply or anything here. Okay, now that I've flipped the reaction, I need to also flip the sign of my enthalpy of formation. This is because the formation reaction was exothermic, and the decomposition, when I flip it, it also takes the energy term to a reactant. So it's going to be an endothermic reaction as written now. So I just need to switch the sign from a negative to a positive. Okay? Now I'm going to do the exact same thing for water, because water is a reactant, and in this reaction here, it's a product. Okay, but I can leave this reaction the same because there's a product here and it's a product in this reaction at the top, what we're looking for. Okay, so when I flip the next reaction for water, I need to flip the sign of the enthalpy of formation, and for the calcium hydroxide one, I'm going to leave it exactly as is. All right, so I've got them all written out here, and now all I need to do is add them up. So when I add them up, I'm actually going to see that the calcium here and the calcium on this side cancel out. So 1 here and 1 here are totally canceled because 1 is a product and 1 is a reactant. Okay, now I have 2 halves of an oxygen, and on this side I have 1 oxygen. Okay, now these also cancel out because they're on opposite sides of my reactions. Last but not least, it's a little hard to see here, but these hydrogens are on opposite sides of reactions. So just like in electrochem, when we were adding half reactions, we can cancel things out. All right, so I cancel out my H's as well, and I'm left with CaO plus water as a liquid makes calcium hydroxide. Okay, so now all I did was add all of those up. So what I'm going to do is add up the enthalpies of formation here. And I'm going to get that they all equal to negative 65.4 kilojoules. So that means that to form 1 mole of calcium hydroxide, 65.4 kilojoules of energy are released. Okay, so in the last example, all we had to do was flip reactions after we've formed them to make our desired reaction. In this case, I didn't actually give you my desired reaction. I said use the following reactions to find the enthalpy change of formation for SO3. So what we need to do is write out the formation reaction for SO3. All right, so in my first reaction here, you can see that 1/8 S8 plus 3/2 O2 makes 1 SO3. But that's a little confusing because there's a lot of fractions involved. Sorry about this. I don't know what just happened there. So what I did was I multiplied this by 8 to give me full numbers. So sometimes you can work in fractional coefficients for compounds. However, it might be easier if we just work in whole numbers and then divide at the end so that we get the reaction for the enthalpy change for 1 SO3. Okay, so this is what we're going to do. We're going to work towards this reaction, and at the end, we'll divide it again to get that. All right, so what I look at here is that I need S8. Okay, so S8 appears in only one reaction up here, okay, and it appears in our first reaction. So I'm going to work with S8 first. Okay, so I just choose something in this reaction and I look for it in the reactions above. Now I'm not going to start with O2, and the reason being is that it appears in 2 reactions. So if you can avoid starting with something that appears twice, you're much better for it. Okay, so I'm going to write out this reaction once because there's 1 S8 and 1 S8 here. Otherwise, I would have to have been dividing by an 1/8, and that's just kind of nasty in terms of fractions throughout. All right, so we have this reaction written out, and now we need to do something about this SO2 because we're making SO3, not SO2. So what I want to do is I want to cancel this out. Now I see SO2 in another reaction here. Okay, now it's a product here, and I need it to be a reactant to cancel out this SO2. As well, I'm looking to make SO3. It needs to be a product, and here it's a reactant. So what I'm going to do is I'm going to flip this reaction here. Okay, and we'll see what that does for us. All right, we've got our full reaction written out here, but the problem is I can't cancel all of my SO2s with this one, nor am I making enough SO3s. So what I need to do is I need to multiply this entire reaction by 4. Okay, but when I multiply the reaction, I also must multiply my enthalpy here. Okay, so this means like that time we were multiplying for the photosynthesis reaction, if we're going to make 6 molecules of glucose, it's going to take 6 times the energy. Just the same if it takes, or if it releases 198.4 kilojoules to make 2 SO3s, it's going to release 4 times as much when I make 8 of them. All right, so I've rewritten my equations one more time here. So I've moved my S8 one down. Okay, just rewritten it as is. And then I also rewrote this equation times 4. So notice when I multiplied by 4, I also had to multiply my enthalpy term by 4. Now I'm ready to cancel and add. So I have 8 SO2s on both sides. They cancel out. Now I can add everybody up and see that S8 and I have 12 oxygens on one side make 8 SO3s. Okay, and so when I add up all my delta H's, I should get negative 3,528 kilojoules. Now that is to make 8 SO3s, but I wanted the enthalpy of formation of 1. So what I can do now is just rewrite my equation one more time and divide everything by 8. All right, and as messy as it is, here's my final answer. 1/8 of a sulfur molecule, because sulfurs come in 8ths, plus 3/2 oxygen makes 1 SO3, and we get that it's negative 441 kilojoules per 1 mole of SO3. You can confirm that by looking at the standard molar enthalpy of formation of SO3 in your booklet. All right. Thermal stability. So all of the enthalpy of formation are reported for the formation of 1 mole of the desired products at SATP. So thermal stability is the ability to resist decomposition. So it would be the opposite of formation. So we would flip the sign of a delta H. Okay? So when a reaction is endothermic, it takes energy to do something. So if we're breaking something up, the more energy it requires, the more stable it will be. Okay, so the more endothermic a reaction, the more stable it is. The more exothermic a reaction, the less stable it is, because as soon as it breaks up, it gives off energy, and that's a positive thing. So the more endothermic a decomposition reaction, the more stable. However, when we usually write them, they're written as a formation. Okay. So the formation one would be more exothermic. But I'm going to write it in terms of the decomposition reaction. Okay, so the more endothermic, the more stable, the more exothermic, the less stable. All right, here's one last challenge problem for you. So I'm going to let you just do that one on your own. We can take it up in class if you'd like. Homework today is page 374, 1 to 5. The challenge is number 6. This is the first line of your demand line, and we will work on the second and third line next time.